Okay, we're in Chapter 1 on functions, and this is Section 1.4, the composition of functions. So we have algebraic expressions we can do on functions, but we always must be aware of our domains. And so that's going to be a key when we start working through these. We have to be aware of what we can and can't do. And that really pertains to square roots and fractions. So if we have something like f plus g of x, what that means is we're going to take f of x plus g of x. And so this and this are interchangeable. So if we're given in this form, we can directly change it to that form, and it's a lot easier sometimes for us to look at it that way. Same goes with the f minus g of x. That's just f of x minus g of x. And then we have f times g of x. Well, that's just f of x times g of x. And finally, f divided by g of x is just the f of x divided by the g of x. And we just plug in whatever the functions f of x and g of x are, and we simplify as needed. And again, we need to be aware of those domains. All right, so here we're given f of x is equal to x squared plus 2x, and that we have g of x is 6 minus x squared. And so what we want to do is find f plus g, f minus g, f times g, and f divided by g. And we need to be sure to determine the domain for each function and put that in interval notation. Well, f plus g of x. Well, that's just f of x plus g of x. So we're going to take this plus this. So we're going to have f plus g of x, and that's going to be x squared plus 2x. And then we're just going to add 6 minus x squared. Now we add this, combine it together, and notice sometimes things cancel. In this case, x squared minus x squared is gone, and so all we're left with is this is equal to 2x plus 6. All right. Now, when we look at that, what would our domain be? What can we plug in for x? Well, pretty much any x is valid here, because no matter if we plug in a negative or a positive, it's going to work. And so our domain is basically going to be from negative infinity to positive infinity. Now, what about f minus g? Well, that's f minus g of x. And so we're going to take f of x, which is x squared plus 2x. We're going to subtract off 6 minus x squared. And so when we simplify that, that's x squared plus 2x. Now we distribute that negative, so then minus 6, and then plus x squared. And so simplifying that, we have x squared plus x squared is 2x squared. Then we have plus 2x, and then we have minus 6. Okay. Now again, here, looking at the domain, no matter what number we plug in here, everything would be valid. If we plug in negative, that's okay. We can square it. We can take it times 2. And so here again, our domain is just negative infinity to positive infinity. Now remember, when I was talking about the domains on a previous one, it really comes into play when you have square roots or you have a fraction. That's where our domain really is going to change. Otherwise, if you notice, everything we've had, it doesn't matter what we plug in here. Our domain is just from negative infinity to positive infinity. All right, so the next one, we're going to take f times g of x. And so we're going to take the x squared plus 2x times the 6 minus x squared, and we're just going to FOIL that. So if you remember FOIL, we take first times first, so it's going to give us 6x squared. Then we'll take the outer, x squared times a negative x squared, so it's going to be a minus x to the 4th. And then our inner, 2x times 6, so that's going to be 12x. And then the last 2x times minus x squared, so that's going to be a minus 2x cubed. Okay, that's a 2. All right, so if we write in decreasing orders of powers, that'll give us a negative x to the 4th minus 2x to the 3rd, and then we have plus 6x squared, and then we have plus 12x. Okay. Now looking again at this one, it doesn't matter what number we plug in here. We can take it to the 4th power, we can take it to the 3rd power, and we can square it, and we can take it times 12. And so our domain in this one also is from negative infinity to positive infinity. Okay. Now the next one though, that's when our domain is going to change, because when you divide, that's where one of the possible changes is going to happen. So what we're going to do is we're going to have f over g of x, well, we're just going to take the f of x, which was the x squared plus 2x, over our g of x, which is 6 minus x squared. Now, can we factor this? Not really. We can factor out an x here, but that's not going to cancel anything here. And factoring this won't have anything that we can cancel really here. And so really now what we have to start looking at is the domain. And so what we want to look at here is this cannot be 0, the whole denominator, because we cannot divide by 0. And so what we're going to do is we're going to take 6 minus x squared, and we're going to say, well, let's set that equal to 0 so we know where it equals 0, and then we'll just say, well, that's the points that it cannot equal. And so to get this, I'm going to take the x squared to the other side. And so if I do that, I have 6 equals x squared. Well, now, to get and solve for x, I'm going to have to take the square root of both sides. And when I do the square root on the left, I have to have plus or minus. So, because I can have a plus square root of 6 and plug it in here and get the same. And I have to take the negative square root. And so then that's the square root of x squared. And so x is equal to plus or minus the square root of 6. Now, these are where it cannot be equal. So this is what it cannot equal. Because if it does, we know that gives us 0 in the denominator. So if we get 0, that's going to be a case where we don't want. And so basically then our domain is going to go from negative infinity up to, well, we have a plus and a negative square root of 6. So it's going to go up to that negative square root of 6. And then we can't include it, so we're going to say union. And then we're going to go from the negative square root of 6. And when we do this, remember that eliminates that as being a point, but we're going up to that point, and then we're going right past that point. And then it goes up to what? Well, then we have up to the square root of 6. And again, we can't use that, so then we'll start here and go from the square root of 6 up to, and now we can go to positive infinity. Okay, so we have 3 pieces. So if we looked at our number line, it'd go from negative infinity up to that negative square root of 6, but it would be an open circle. And then from there to square root of 6, we have another open circle. And then from there, it would go all the way to positive infinity. Okay, so that one is the key one where we have something that's different for our domain. Now, the next thing we're going to look at is the composition of functions. So this is one more thing. We had the f plus, f minus, f times, and the f divided by the g's. Now we're going to have f of g. And so this is f of g of x. And what that means is we're going to take and plug in g of x into f, which means we've plugged in some x value into g. We get that value out. Then we plug that into the x for f, and then we get another value out, and that's going to be our f of g of x. And as I said, it's f of g of x is how this is read directly. And again, what we're doing is just plugging x first into g, then whatever that output goes into f, and then that gives you a final output of whatever that is. Now, sometimes you're going to get numbers, sometimes you're just going to get an expression. And so let's see here how these are not commutative. So if we take f of g of x, that's not going to be equal to g of f of x. And this is the example kind of to show you why that is the case. It's not commutative. So what we're going to do is we're going to plug x into f, okay? Well, f is 2 times x. And remember, whatever g of x is what's going to go there. Well, g of x is 3 minus x. And then we have plus 1. So now we have to distribute here. So that's going to give us 6 minus 2x plus 1. And so that's going to give us 7 minus 2x. Okay, so that's going to be what f of g of x is equal to. Now what is f of x plugged into g of x? So g of f of x. Well, g of x is 3 minus x. Well, x now is going to be f of x. So that's 2x plus 1. And so then we're going to take and distribute here. So it's going to be 3 minus 2x minus 1. And so that gives us 3 minus 1 is 2 minus 2x. And so that is going to be what g of f of x is. And if you notice, those are not equal. Therefore, we are not commutative here. So we can't just go from one to the other and say they're equal. You actually have to find the other one if they ask you to find both f of g of x as well as g of f of x. All right, now we're going to use that example as far as how f of g of x and g of f of x works, and we're going to do it with tables. So we're going to evaluate composite functions with tables. And so what we have to do is we have to first evaluate the inner function using the starting input, whatever that's given to us, and then use the inner function's output as the input for the outer function. Then we find out what that output is, and that's going to be our answer. So it's complicated, but what we're going to do is what we're going to do is just do some examples. So our x here is 8. So we look here and we find 8. And we want g of 8. Well, g of 8 is going to be 4. So our first thing we're going to do is find f of, now we have g of 8 is equal to 4. So that's f of 4. Because we had g of 8 equals 4. Now we need to find out what f of 4 is. Well, x now is 4, and so if f of x, that gives us 4, and so that is going to be our answer. So first we had to find out what g of 8 was. That was our 4. Plug that into f, and f of 4 is equal to 4. Okay, so that then would be our final answer. So this one, let's write it out this way. Let's find out what g of 5 is first. Well, 5 is x, and g of that is going to give us 8. So now we need to take that 8 and plug it into f, and so we need f of 8. Well, now we go x is equal to 8, and we need to find f of that, which is 9. And then that would be our answer for f of g of 5. Now let's do this one. Now we're looking for first f of 5. Well, f of 5, we find x is 5, and f of that is 0. So that's 0. So now we need to find g of 0 because we're plugging this into the g. So x now is 0. We're finding the g of 0, and that's equal to 9. Okay, and so that would be our solution on that one. All right, so what about g of 2? So what we're going to do is we're going to plug in 2 into g, get an output, and then plug that back into g and see what that output is. So first, g of 2. Well, here's 2, and g of it is 6, so that is g of 2. So now we need to find g of 6 because we want a g of 2. And so now we find 6 for x, and the g of it is 7. And so that would be then our solution to that one. And finally, we have to do, of course, the f's. So we need to find f of 7 first. Again, x is 7. So f of that, remember, we'll go to the f row. So that's a 1. So that's equal to 1. So now we're going to plug that into f again. So we f of 1. So we go up to tier 1, find f of that. That's equal to 6. And then that is our final answer. So again, with tables, you just have to go and find whatever it's asking for initially. So, the g of 8, so we plug 8 into g, get that value, and then we plug in whatever that output is into f, and then that gives us the next output as f of 4 in that case. Okay. All right, so we can also do this with graphs. So basically what we're going to do is read input and output from the x and y axes. So basically they're going to have to give you graphs that are easy enough to read to get whole numbers most likely. So you're going to locate the given input to do the inner function, whatever that is, f or g or h or whatever, and do that on the x-axis of the graph. Then you're going to read the output of that inner function from the y-axis. Okay, so input is x, output is y. And then we're going to locate the inner function output on the x-axis of the graph on the outer function. And then what we're going to do is we're going to read the output of that on the y-axis, and that's going to be the output of the composite function. So this is easier said than done. So that's the words. So now let's kind of look at it. So we've got 3 graphs. We've got f of x, we've got g of x, and we've got h of x. So we want to find f of 1 first. So f of 1, well, remember, x is 1, so if we plug in 1 for x, what do we get? Well, that comes up and that gives us a 1 as the output. Okay, so then f of 1 is equal to 1. And so now we need to have what is g of 1, because now we've found that f of 1 is 1, so now we need to find g of f of 1, so that's 1. Well, here's our g function, so it's a 1 for the x. What comes out as output? Well, that's equal to 1 as well. So that then is our final evaluated g of f of 1. All right, what about the next one? We have g of 4. Well, first let's find what g of 4 is. Well, here's our g function. 4 is x, then our output is 2. So g of 4 is equal to 2. So now we plug that into f. So f of 2 is equal to what? Well, we plug in 2 for f. So here's 2, here's f. Come up, it hits a 4 it looks like, and then output is 4. And then that would be our final value for this one. Again, just reading off the graphs instead of the table. It's pretty much the same thing. It's not hard. You just have to follow the inputs, outputs, and plug it into the next one, then input, output, and get your final answer. All right, so here we're going to find first f of a negative 2. Well, here is f, negative 2, output is 4. So that's equal to 4. Now we want to plug that into h, so we want to find what h of 4 is. So now we go all the way over here to h. We want to find that h of 4, that's equal to 4 as well. And then that would be our final output. Now the next one we have three things we have to do. We have to take h of 4, whatever that is, we plug it into g, then we take g of that, and then whatever that is, we plug that into f, and we get out a value. So let's do this in order. So h of 4. Well, we just said that that was 4, so that one's pretty easy. So now we plug that into g, so now we need g of 4. Well, g of 4 is 2. And now we want f of 2. That's our final one here. And so f of 2, so we go x is 2, come up here, and the output here is 4. And so then that would be our final value on that one. Okay, so again, it's not much different than tables, except here you actually just have to read the numbers off of the graphs instead of out of a table. All right, here what we're going to do is we're going to evaluate composition functions with formulas. So it's kind of like the same thing, because each one of these we could graph it, and then we could get a value off. We could plug in some value for x, get a value out off of the graph, or what we can do is we can plug the values into the functions themselves and then get a value out, and then plug it into the next function and get a value out. And so it's just doing the math instead of looking at a graph or looking at a table. So they want us to find f of g of 0 and g of f of 0. So basically we're plugging in 0 for g first, getting that, and then finding what f of that is. And then the other one we're going to plug in 0 for f, get that value, and then plug that into g, and then get the value out there. So let's first do the g of 0. Okay, so we're going to do the inside here. Well, g of 0, if we plug 0 in here, all we get is 4. Okay, so now what we want to do is find f of 4. Okay, because we plugged in 0, we got 4. Now we want f of 4. So now we just plug in x is 4 here. So that's going to be 5 times 4 plus 7. Well, 5 times 4 is 20 plus 7 is 27. And so that would be our first one, which was f of g of 0. Now, if we want to do g of f of 0, we know it shouldn't be the same. And so let's see, if we plug in 0 for f, well, 0 times 5 is 0 plus 7. So f of 0 is equal to 7. Now we want g of 7. So now we have to plug in 7 here. And so we take and have 4 minus 2 times 7 squared. So that's going to be 4 minus 2 times 49. And 49 times 2 is going to be what? Negative 98 plus 4. So it's going to be negative 94. And then that would be our value for g of f of 0. All right. And again, not much different. I mean, if we had a table, we would get these values out directly. We wouldn't actually have to plug in numbers. We just look at a table. Or if we had graphs, we could do the same thing. We could just look at the graph and get the numbers out directly, and we wouldn't have to do the calculations. But this time we're doing formulas, so we actually have to do the calculation. All right, so if we plug in and we go down here and we're still doing f of g of 0. So what is g of 0? Okay, well, g of 0, well, that goes to 0. We just get 12. So now we want f of 12. So we plug in 12 here, we get the square root of 12 plus 4, which is the square root of 16, which is just 4. Okay. Now what if we do f of 0 first? Okay, well, f of 0, if we plug in 0 here, it's going to be the square root of 4, which is 2. And then we want g of 2. Well, that's going to be 12 minus 2 cubed. Well, 2 cubed is 8, so 12 minus 8, that's equal to 4. Okay, so in both cases on this one, we get the same answer, but that's okay. But the normal is you should get different answers as far as going for the f of g of 0 and g of f of 0. All right. One last one. So let's say we want f of g of 0 here and g of f of 0 in this column. All right, so g of 0 first. All right, g of 0, well, 4 times 0 is 0, plus 3 is 3. Then we want f of 3. And if we plug in 3 here, we get 1 over 3 plus 2, which is 5. And then that would be our final answer. Now in this one, what if we plug in 0 for x first on f? Well, 0 here, that gives us just 1/2. And then g of 1/2 is just going to be 4 times 1/2 plus 3. Well, half of 4 is 2, plus 3 is 5. And that would be our answer there. All right. So that's, again, using the formulas instead of a graph or a table. But all three basically are interchangeable if you think about it, because the table is going to have all of these calculations done for you. The graphs are just going to be something you can read off the values for the calculations, and these you actually do the calculations. All right, so here we're going to find the domain of a composite function. So f of g of x is a set of those input x's in the domain of g for which g of x is in the domain of f. So basically we have to find the domain of g, find the domain of f, and find the input x's or inputs x in the domain of g for which g of x is in our domain of f. And this is all going to make sense once we start doing it. So that is basically we're going to exclude any of the inputs x from the domain g where g of x is not in the domain of f. And so then that resulting set will be in the domain of f of g. Okay, so let's look at this one as an example here. So if we look at directly here, what is going to be the domain of this one just as it sits, f of x? Well, what we have to have under here, it has to be greater than or equal to 0, or greater than or equal to 0. And so we set this greater than or equal to 0. So if we set that, that means x is going to be greater than or equal to 4, or negative 4. And so basically here we're going to have 4 to positive infinity. So anything in there is going to work, okay? Or actually negative 4, sorry, where'd the negative go? And here we're going to set this greater than or equal to 0. And so when you take the other side here, that's going to be x is going to be less than or equal to 5. And so our domain here, less than or equal to a 5, will have something like that. Okay, but we want to find the domain of f of g of x. And so what we're going to do is we're going to plug in this into here. So f of g of x looks like the square root of 5 minus x plus 4. Okay, so what we know here basically is that everything under here has to be greater than or equal to 0. Well, we found that domain already. And so basically, as long as that's greater than or equal to 0, this will be a positive number. And then a positive plus a positive, that's going to be positive. So really, our whole limiting thing is what this is. Well, we found that domain. And so the domain of the composite function is going to be the same. It's going to be from negative infinity to 5. And it's going to include that 5, so it's going to have a bracket. Okay. And again, all we did was we set these like this. We added x, and so 5 is greater than or equal to x, or x is less than or equal to 5. And so when you do that, that's everything less than or equal to 5. And so that will be our domain of the composite function of f here and g here. Now, the key thing to note is this one's, the domain here is not all inclusive of this, because we can only go up to -4, or down to -4 here, but this one we start at 5 and we can go all the way to negative infinity. So our domain here doesn't always necessarily relate to what the domain of f of x is, and that's kind of, this is a key example to show that maybe sometimes the domain here will override what our domain is here. All right, what about this one? So if we look at this one, we have two things. Well, we know that we can't have 0 here. So x minus 2 cannot equal 0. And so x cannot equal 2. We know that one. And here, x plus 4 has to be greater than or equal to 0. So x has to be greater than or equal to a -4. Okay. And so what do we have with that? So with f of g of x, that's going to be f of g of x equals, now we're going to plug this down into here, and so we're going to get 1 over the square root of x plus 4 and then minus 2. Okay, so what do we have here? Well, we know that x has to be greater than or equal to a -4, and then we're going to get a positive number here. And the other key thing is the only positive number it cannot equal is, we know that that cannot equal a positive 2, because if it does, basically if when x is 0, that's going to become 0 here. So that gives us that x cannot equal 0. So if x is equal to 0 here, then this is going to not work. So our key thing out of that is, when we know this is 0, we get square root of 4, which is 2, minus 2 is 0. So that we know that this cannot equal 2, which gives x cannot equal 0. We also know that it has to be greater than or equal to a -4 to make that 0. And so what we have is, we have two pieces. We have this piece and we have this piece. And so what we have then is, oops, that's going to be greater than or equal to, not just strictly, greater than or equal to -4. So that's going to be a bracket from -4 up to, well, we know it cannot equal 0, because if it equals 0, we get a 0 in the denominator. And so we'll have a parenthesis, union, and we'll go from 0. And now it can be any number greater than that. So all the way up to positive infinity. So this then would be, I guess we go out here and we'll say our domain is equal to that. Okay, so it goes from -4 to 0, union was 0 to positive infinity. So we had to kind of come up with different pieces. Here we knew x could not equal 2. Well, where is it not equal to 2? Well, that's when x is equal to 0. And so we know that that's the case when you have f of g of x. And then we also know that what's under here has to fit this. And so putting those two together, we get this here. All right, so now we're going to do a couple of combinations. We're going to have this q of x divided by h of x. We're going to have q of x, q of h of x. We're going to do a composite that way. And then we're going to do the composite the other way, h of q of x. All right, so let's write these out. What is q of x? Well, q of x is 1 over the square root of x divided by h of x, which is x squared minus 9. All right. So with this, we have a couple things we have to consider. We know that this fraction, x, cannot equal 0. Now with this one, we know that x squared minus 9 cannot equal 0. So we have kind of two fractions here. And now with this one, x squared cannot equal 9. And so when we take the square root of that and plus or minus the square of that, we get x cannot equal 3 or x cannot equal a negative 3. Okay, so we have the 0, the 3, and the negative 3. And so what we're going to do is on these, we're going to start kind of doing testing. And so here's negative 3. Let's call that positive 3. And let's call that 0. And so we want to know where this domain is going to fit in, because at this point, we know that these points don't work. But let's go ahead and consider some point out here. This is going to be our test here. Let's call that a test here. Let's call that a test here. And we'll do a test here. Okay, so probably shouldn't use test, but that's what we're going to use. And if we use a negative 4 here, is that going to work? Well, a negative 4 gives the square root of negative 4, so that's false. Okay. Now, how about a negative 2? Well, that's still going to be false. Well, how about a positive 2? Well, positive 2, we can plug that in and that will work. And a positive 2 here will work too, because it's not a 3 or negative 3 and cannot be 0. So this is a yes. So this area here will work. What about, say, a 4? Well, square root of 4 is 2, so that works. 4 squared, 16 minus 9, so that works. So that area works as well. Okay. So basically, everything over here does not work. Everything from here to here doesn't work, but this region, you know, it works except for that open circle here. And it doesn't work here. This basically is an open circle here too, if you think about it, because it's one of the points that it cannot equal. And so what we're going to do is we're going to go from 0 to 3, union 3 to positive infinity. And so it's true in this area, it's true in this area, but it's not true at the 0 and the 3. And it's also not true at the negative 3 here as well. So that's going to be our area where we have a true statement, and that's going to be our domain. Okay. All right, what about q of h of x? And so what does that mean? We're going to plug in h of x into q. So this is h of x. We're going to plug that into q. And so that's going to give us 1 over the square root of x squared minus 9. Okay. So what do we have here? 1 over x squared minus 9. What can we do there? Well, we know that everything under the here has to be positive, because we can't take the square root of a negative, but we can't equal 0 either. And so that means we're going to have x squared minus 9 is strictly greater than 0. Okay. Because if we normally would do, you know, greater than or equal to, but this time, because we can't have 0 in the denominator, it's just strictly greater than. So then that gives us x squared is greater than the 9. And so when we take the square root of both sides, we're going to get x is going to be greater than 3, or x is going to be less than negative 3. And that has to do with how inequalities work with the greater than and taking square roots. And if you think about it, we have what this, what the x squared plus 9 is a parabola. And it's basically has been shifted down nine units. We'll get to that in a little while. It's been shifted down 9. And so where is it going to be 0? It's going to be 0 at this point, and it's going to be 0 at this point, and that's at negative 3 and positive 3. And so basically anything greater than the positive 3 will work, and anything less than the negative 3 is going to work. And so that's going to be kind of our restriction here. And so with that restriction, then we can really just write our thing, our domain. And so it's going to go from negative infinity up to a negative 3, and that's going to be in union with, and then where our other one is going to go over this way, it's going to be from 3 to positive infinity. And so that then will make this a true statement. So anything less than a negative 3 will work, anything greater than a positive 3 will work, but it cannot equal those, but it has to be greater than or less than those values. Okay. Now what about h of q of x? Okay, well, now we're plugging in q of x into h of x. And so that's going to give us 1 over the square root of x squared minus 9. Well, here we only have one thing to worry about, the square root of x. And what do we know about that? Well, x here has to be greater than 0, cannot be equal to 0, has to be anything greater than. So we have a strictly 0 to positive infinity is going to be our domain. Okay, so we just know that that's going to be where it works, and so anything greater than that's going to work as well. All right, now the next thing we're going to look at is how to decompose functions. We composed them now. Now let's look at it going the other direction. How do we decompose these? Well, decomposing a composite function into component functions, there's many ways to do it, and you're going to get two functions. We start with some h of x, and we're going to get some f of g of x out. And what we need to do is we need to find out what g of x is, and then we need to find out what f of x is. And so there's no wrong answers as long as what you do works here. So I'm going to pick out the most obvious ones is how I do it. You can maybe be more exotic, but I think finding just the simplest ones is probably the easiest way to go. So what we're doing is we're having f of g of x. So we need to find some g of x that we can plug into some f of x. So we need a g of x and we need an f of x. All right. Well, what can we see here? Well, this is some quantity x plus 2 squared. Well, what does it look like we've done? Well, if we kind of go back here, what did we do here? Well, we plugged in what's under the square root into the function 1 over the square root of x. So we just plugged that in. And the same thing goes here when we did this one. We just plugged in 1 over the square root of x into this function here. So what could we say g of x is? We could say it's what's under here. We could say that's just x plus 2. And what do we plug that function into? Well, what is it if we take out x plus 2 and plug that as x? Well, it's just x squared. And so that's what I would use for my g of x and f of x, because what it says is I'm going to plug g of x, x plus 2, into my f of x. So if I plug that into here, I get this back out. Okay. Well, what about this one? Well, in a similar manner, we have 3 over x minus 5. So g of x, f of x. Well, if I think about this, this could be 3 over x is my original function, f of x. And what did I plug into it? I plugged in x minus 5 into that x. So basically, I'm taking this whole thing here as my g of x. And I'm saying, well, here was my x initially, and it was 3 over that. And then once I plug this into here, I get my 3 over x minus 5 out again. Now the same thing goes here. Here I've got a cubed root of x, and I have 4 plus that. Well, I think what I would do is I'm going to say, well, let's call 4 plus x my f of x. And then what did I plug into it? Well, I plugged into it the cubed root of x. Okay, so my g of x I plug in to here, and I get 4 plus the cube root of x then. And again, you could choose other options. It all depends on how you want to look at it, but I'm trying to do the easiest ones possible, and that's what I see as the easiest ones possible. All right, of course we have to have our application problems with these. And so we're going to do function composition to get these final answers, to get the final, in this case, equation they want us to use. And so a store offers a customer a 30% discount on the price X of a selected item. Then the store takes off an additional 15% at the cash register. So, when you pick up the item off the shelf, we get a 30% off that original price X. And then the store at the cash register takes off another 15% of this discounted price. And what we want to do is we want to write a price function P of X that computes the final price of the item in terms of the original price X. So we want to use function composition to find our answer. So what we need to do is we have to think about what is the discount formula. And so this is something that's going to be able to help us do our initial discount and our additional discount. So if we think about that, how is the sale price calculated? So a sale price, let's call it S of X. Well, that's just done by taking our original price times how much the discount was. And it's going to be 1 minus that whatever that rate is. So let's call it rate 1 because we have two rates. We have this one and we have this one. And 1 minus, 30% is going to be 1 minus 0.3, or that's going to be 70% of the original price is what we pay. And so that's kind of how a discount works. It's 70% of the original price is going to be the sale price, and that's the original sale price of 30% off. Then, once we get to the cash register, they take off another 15%, and they want to call it that one P of X. So P of X is then going to be our sale price, S of X, and then it's going to be times, now we have to discount off it, so it's going to be 1 minus our R2 this time. I'm going to call it R2. And so that's going to be what our final price is. But now what I'm going to do is I'm going to substitute this in here so I get a whole single equation. P of X equals X, original price, times 1 minus R1 times 1 minus R2. And then that will be my function I'm going to use. Now, since they do give us our rate 1 and our rate 2, we can plug those in. And so P of X equals X times, well, 1 minus, and again, we have to put these in decimals, so that's 0.3. Well, that's going to give us 0.7. And here we have 1 minus 0.15, so that's going to be 0.85. And then given whatever price our original price was, if we take it times 0.7 times 0.85, that will be our final function price P of X, okay? And so those are the ways to do it. First, you have to know how to get the discount, and then you have to apply the discount to the you have to apply a new discount to the original discount, and then you just plug all of it together to get your formula. And then I plugged in the numbers just because they gave us the numbers, and I got that final function here, P of X. All right, so this one says a forest fire leaves behind an area of grass burned in an expanding circular pattern. Okay, so we got a circle, and so that's kind of the pattern we have. Now, if the radius of the circle is increasing with time according to the formula R of t equals 2t plus 1, express the burn area as a function of time. So we've got the R. Now, what do we know about this? Because it's asking about the area. What's the area of a circle? Well, the area of a circle is equal to pi r squared. Okay, so we'll need that. We need our function R of t equals 2t plus 1. And now we just kind of plug everything together. So if we need to have the area as a function of time, well, here's our radius as the function of time. So if we plug that in here, we'll have A of t is equal to pi times, and now we have 2t plus 1, and that's squared. Now, do we need to multiply this out? I don't think so, because we can consider that our radius times the pi. And so basically, again, all we've done was taken that r, plugged it into our pi r squared equation, and said, okay, well, now a is a function of t because this is a function of t. And so now we have our area of that circle burning as a function of time. So, after whatever is it in minutes, so after 2 minutes, that'd be 2 times 2 is going to give us 4, plus 1 is 5, 5 squared is 25, pi is how the area is going to be at that point in time. All right, so that's all I have for this part. I'll do another part to give a few more examples.